So part one is data collection. Within data collection, we will cover data acquisition, data labeling, and improving existing data. So recently, my students and I performed a survey on data collection techniques for machine learning. And you can see this taxonomy we came up with, and there are many individual techniques. Now, the interesting thing to see here is that if you look at the leaf node techniques, we've colored them in red and blue. Now, blue techniques mean that they come from the machine learning, computer vision, and natural language processing communities. These are the techniques like active learning, semi-supervised learning, and transfer learning. The techniques that are colored in red, on the other hand, come from the data management community. For example, dataset searching is clearly a database problem. Data programming was also proposed from the database community. Data cleaning is also a heavily studied problem in this community. So you can see that, interestingly, there is a convergence of data management and machine learning techniques, almost with the same ratio. So we came up with this data collection flowchart that can help any user to find the right data collection technique to use for his or her application. So the first question, we start from the top left, is whether you have enough data. So if you don't have data, then here are some options. Here are some techniques you can use. If you do have data, then the next question is whether you want to collect more labels. Labels are important when you're doing supervised learning, where the goal is to train a model that makes predictions. If you also have enough labels, then another useful operation is to improve your data and labels. And so we have techniques here as well. So let's go through this in more detail. Suppose you don't have enough data, what do? Well, the first option is to discover new data sets or augment whatever you have. Otherwise, you can generate your own data sets. So data discovery is the problem of indexing and searching data sets that exist either in corporate data lakes or the web. So here are two representative examples of those two cases. So goods system in Google is used to search Google's data lake, which consists of at least tens of billions of data sets. Now, the big challenge here is that there are many data sources. So there are file systems, but also big tables and spanners. And there is no way that all of this data can be consolidated in a single place. So you can ask for the dataset owners to move their data. So what Goods does instead is it takes a post hoc approach where it crawls the data sets and extracts metadata and maintains the central dataset catalog. And this doesn't require any work from the dataset owners. So here, each entry contains metadata about one dataset. In this case, there is a dataset called Bigtable Foo, which has this size and has a provenance where it's written by some job and it's read by some job, and it has the following schema. Now, on top of this dataset catalog, Goods system provides search, monitoring, and annotation. Now, recently, there is this open version of Goods to the world called Google Dataset Search, which helps you search for science datasets primarily. So if you go to the website, you can type keywords like coronavirus COVID-19. And currently, dataset search will give you more than 100 datasets. Now, in comparison to the internal Goods system, the public version assumes an open ecosystem where the dataset owners can publish semantically enhanced metadata of their own sites. So once you publish your metadata, Google Dataset Search crawls that information automatically and builds an index out of it. More recently, these data discovery tools have become more interactive. So Junio is an interactive data science tool built on top of Jupyter Notebooks, which is a popular platform for data science. So the workflow is as follows. So here's the user. Here's a notebook that has a workflow of cells. And the user can pose a query asking, searching for related tables for a given table T. Then the server search engine searches the data lake, maybe other notebooks, and returns a ranked list of related tables. And the user can choose to import some of the tables like T prime, and then the server inserts a new cell to generate the code to import table T prime. And so here the key technical challenge is finding the related tables. And Junio uses measures that use the row column overlaps, provenance information. This intuitively captures the purpose of creating each data set, and approximate matching measures. So in addition to searching for new data sets, you can also augment your existing data set. So the goal here is to complement existing data sets by integrating them with some external or generated data. So a very popular method for generating data used in the machine learning community is generative adversarial networks, or also known as GANs. So here we have, we start from a training set that has real data. So these are just images of digits, like the MNIST data set. And there are two components here. There's a generator that generates fake data that is realistic, using some random noise as an input. And there's a discriminator that tries to distinguish the real data from above from the fake data from the generator. And now the problem is to compete these two, the generator and discriminator, such that the generator tries to generate data that's realistic enough to trick the discriminator, while the discriminator tries to be really good at distinguishing the two cases. And so if the training is done properly, then what you have is this generator that can generate realistic fake data. So that's a popular method for increasing amounts of data. Now, one limitation of GANs is that you can't go like way beyond whatever data you already have, because there's no way that the GAN will automatically figure out how to generate very different data. And so policies is a way to complement that approach, where you can apply various custom transformations by some domain experts, as long as the data remains realistic. So here's an example for policies. Starting from this image, you can apply, maybe change the brightness of this image, or do some resizing, invert it and rotate it. And as long as these images are acceptable, then you've created some new data. Now, auto-augment is a recent system that tries to automate this process. So the idea is to have this controller that suggests a strategy for applying some operations or policies with some probability and magnitude on the data. And then the system trains a child model on this augmented data to get and measures the accuracy on some validation set. And this result is used to decide whether this strategy is useful or not. So if the data is totally off, then we don't want to use this strategy anymore. If it's useful, if the accuracy is okay, then the controller will keep on using this strategy. We'll keep it. Now, another option for collecting or acquiring new data is to generate data yourself. So you can use crowdsourcing platforms like Amazon Mechanical Turk, where you can create tasks and pay human workers to collect data for you. In this example, this is a task where that is asking workers to find restaurant information. And this is a very, very common approach for acquiring new data. So now, if you have enough data, the next question is whether you want more labels. So again, labeling is very important in a supervised learning setting where you want to train a model for doing predictions by training on the labels. Now, there are three cases I want to consider. The first is if you have some labels to use, then there are self-learning techniques that can exploit whatever labels you have to label the rest of the unlabeled data. Now, if you don't have such labels, but if you have some budget, then you can use crowdsourcing, just like in data acquisition. If you don't have such funds, then there is an approach called weak supervision, where the idea is to generate labels automatically that are not as accurate as manual labels, but you can produce them at scale. And so sometimes that compensates for the slight lack of accuracy. So I can't emphasize enough how important data labeling is. We personally, I've worked with several companies in the industry, and their number one complaint is finding labeled data. This is a serious problem, especially if the application is very narrow. So in manufacturing, for example, you may have this pipeline where you have a smart factory, you have all these images of products, and you want to see which ones have defects, which ones are okay. In order to do that automatically, you need to train a model using lots of labeled data. So someone has to go through the images and mark some of them as okay, some others as defective. Then this model can automatically determine whether which ones are okay, defective. Now the problem is, very few people know about this narrow application, right? So the domain experts that label this data are highly specialized, and they actually require a demand for high salaries. So we've heard of six-figure salaries, for example. And so data labeling is indeed a major bottleneck for using deep learning in many companies. So if you already have some labeled data to use, then you can try out self-labeling techniques, where the idea is to label the rest of the unlabeled data. So some of you might be thinking of semi-supervised learning. So indeed, self-labeling is one type of semi-supervised learning where you want to utilize labeled data and a lot of unlabeled data to train an accurate model. And the simplest technique here is called self-training, where you start from a training set, you train a model on whatever you have, and then you apply it to unlabeled data. And then among the predictions that have the highest confidence, you trust them and add them into the training set, and hopefully that will result in a better model. Now, this is not the best, or necessarily the best approach. There's a question of whether you should trust high confidence, and there are many other techniques available. Now, another approach is to use crowdsourcing. So if you don't have any labels to start with, but you have some funds, then you can use platforms like Amazon Mechanical Turk to perform labeling. And since labeling is such an important service task, there are actually services that are specialized for that as well. So there's Amazon SageMaker Ground Truth, and there's Google Cloud Labeling. So the below diagram shows the SageMaker Ground Truth workflow. So you start with raw data, and you choose labeling tasks, and then you recruit labelers. These labelers are assisted with UI and some assistive labeling features to label your data. So all of this is done for you in the same service. The last resort is to rely on domain experts, but again, this can be really expensive, and especially in manufacturing, we've heard of very high salaries for using these people. So it's good to avoid this option as much as possible. Now, active learning is a very useful technique to reduce this crowdsourcing cost. So here the idea is to ask human labelers to label difficult examples that, when answered, are likely to improve model accuracy the most. So this diagram says that is the same, describes that. You start from unlabeled data. You ask human annotators or some oracle to label the important examples and then add them back to the labeled training set, which can be used to train better models. And so there are lots of techniques here, and I refer to this survey by Settles. Now, in the case where you don't have enough funds to simply use crowdsourcing for labeling, another attractive alternative is weak supervision. So here the idea is to semi-automatically generate labels that are not perfect, and therefore we use the word weak, but at scale where the larger volume compensates for lower label quality. And this is useful for applications with few or no labels. So the diagram below shows a performance of a weak supervision system called Snorkel Drybell on some Google workloads. So the details of the application are not important, but this trend is. So the x-axis shows the number of training examples available. Y-axis shows the accuracy, F1 in this case. And the blue plot is the performance of the fully supervised system that uses the label data. And you can see that as there's more labels, then the performance goes up. Now, Snorkel Drybell, the dotted orange line, on the other hand, does not require labels. It instead requires so-called labeling functions that can be used to generate weak labels on unlabeled data. So as long as you have these functions and the functions have a certain quality, then Snorkel Drybell has good performance. It actually has a constant performance. So you can see that if you have lots of labels, then you should probably use a supervised approach. But if you don't have labels or only have few of them, then Snorkel Drybell performs better. So data programming is the standard technique for weak supervision. The idea here is to implement many labeling functions, maybe 10 to 100, that can be used to generate weak labels. And Snorkel, the Snorkel system, is the seminal system for data programming. So here's an example of labeling functions. Let's say that you want to perform spam detection. Now, labeling function 1, works as follows. It looks for certain spam keywords like subscribe. And if so, it guesses that the text is spammy. This itself is not perfect, but it's useful to some degree. Labeling function 2 checks if the text is too short. And the intuition is that short text is an indicator of spam. And labeling function 3 checks if the text is not polarized or subjective. And again, this is a good signal for determining spam. And there can be other labeling functions as well. So then what Snorkel does is it combines all of these labeling functions in one generative model. So intuitively, it's taking the consensus of these functions. And given some unlabeled data, it can generate probabilistic labels, the labels that it thinks are likely to be for each of the examples. And these probabilistic labels are used to train a final model, a discriminative model, like a deep neural network or a convolutional neural network. And assuming that these labeling functions are not, have a certain quality, then it's guaranteed there are theoretical results that this discriminative model, it has high performance. So once you have enough labels, then another option you might want to consider is to improve your existing data and labels, or even your existing model. So improving labels can really improve model accuracy, where simply acquiring more data cannot. And so here's an example by Sheng et al. A couple of years ago, demonstrating that point. So the x-axis here is the number of examples, training examples, and the y-axis is the accuracy of the trained model. And there are several models considered where Q is the parameter for the quality of the data. So low number means lower quality data. And you can see that as the data quality decreases, well, even if you use more data, the accuracy of the model does not increase from some points. So it plateaus here and here. So in this case, the only way to improve the model accuracy is to improve the label quality, which can be done by relabeling techniques like labeling multiple times and taking a majority vote, for example. And so it's very important that your data is of a certain quality, because if not, then however much data you have, it may even have a negative effect in model accuracy. You can also improve the quality of your data, and we're going to cover this topic in the data cleaning part of this tutorial. Now, another method I wanted to just mention is improving existing models. So there's an entire research field called transfer learning, where the idea is to reuse a pre-trained model across different tasks. So for example, let's say that you want to train a text classifier to determine whether sentences are questions or just non-questions. Now, in order to train this classifier, you probably need to have lots of labeled data, and it's going to be a challenging task. But if you already have a model that can help, then the idea is, why not use this model? So let's say that there is this embedding model that can generate for each sentence these embeddings, which are just vectors of real numbers that intuitively capture the contents of the sentence. And so once you have these features, then it becomes much easier to train a question classifier to distinguish questions versus non-questions. So whenever you're training a model, it's a good idea to be aware of any similar model that you can just train on top of. In summary, there is this interesting convergence of techniques from the big data and machine learning communities for data collection. And here, one needs to acquire data, label data, and/or improve existing data.